Hello, AP Chemistry students, and welcome to part 1 of Unit 5. This whole unit is going to be about kinetics, and today we're going to be focusing on rates and rate laws, which is covered by sections 5.1 to 5.3 and 5.5 to 5.6. So our learning objectives here are to explain the relationship between the rate of a chemical reaction and the experimental parameters, to represent experimental data with a consistent rate law expression, to identify the rate law expression of a chemical reaction using data that show how the concentrations of reaction species change over time, to explain the relationship between the rate of an elementary reaction and the frequency, energy, and orientation of molecular collisions, and then to represent the activation energy and overall energy change in an elementary reaction using a reaction energy profile. So the main idea behind all of this is thinking about rates. And a rate is a change in something over time. You could think about the speed you drive at your car as a rate. You're moving a certain amount of distance. You have a certain amount of change of displacement over an amount of time. In chemistry, we're going to be focused on reaction rates that are defined by the change in concentration of a substance as a function of time. And we're usually going to be measuring rates in units of molar per second. So we divide the amount of concentration that is either created or used up, depending on if we were looking at a reactant or a product, divided by the amount of time that has passed. And we'll notice that for a change, if it's the rate of a reactant, it's going to be negative because the concentration is going to be decreasing as the reactants are used up to make products. And then by the same logic, the rates for products are going to be positive because the concentration is being formed in the process of the reaction. And overall, there's a stoichiometric relationship between the rates of different reactants that looks like this overall thing above. The overall rate for the reaction as written is going to be equal to the negative 1 over the coefficient of one of the reactants is equal to 1 over the negative of the coefficient of the other reactant, which is equal to the positive 1 over the coefficient of the products, and so forth. And this is just a really fancy way of saying that the rates of the individual components can be compared by their mole ratios. For example, say that the coefficient for capital A was 1 and the coefficient for capital B was 2. We could say that the rates of A and B, respectively, have this following relationship. That the rate of A is going to be equal to 1/2 of the rate of B. And that makes sense because B has 2 as a coefficient and needs to be used up twice as fast as A because we need to use 2 B's for every 1 A in our reaction. So that makes sense that the rate of A is going to be half the disappearance of B and that the disappearance of B is going to be twice that of A. And since these are both reactants, they're both going to have negative rates. And whatever the coefficients of the products are also going to be related in the same way, but as a positive rate. So let's consider the following reaction. We have 3 sodium hydroxide plus phosphoric acid making sodium phosphate and 3 water molecules, which is a acid-base neutralization reaction. So say that our phosphoric acid had a concentration of 0.3 molar, and we're reacting with excess sodium hydroxide solution. So we don't really care what the starting concentration of that is. We find that the reaction takes 10 seconds, and we want to know what the reaction rates for all of the chemicals in the process are. So since we have a specific concentration of the phosphoric acid, and we know that we are neutralizing all of it, we can know that all of it is going to react in those 10 seconds. So we're going to go from 0.3 molar to 0 molar. So our change in concentration for the phosphoric acid is going to be negative 0.3 molar. And then if we divide that by the time in seconds, we end up with negative 0.03 molar per second as our reaction rate. And then, like I was saying before, I can compare this reaction rate to the other chemicals in the same equation through their mole ratios. I know that the rate of reaction for the sodium hydroxide is going to be 3 times more because we need 3 sodium hydroxides for every 1 phosphoric acid. So I also know since it's a reactant that it's also going to have a negative rate. So I'm basically multiplying this by 3 over 1, which would be the mole ratio between phosphoric acid and sodium hydroxide. So I end up with a sodium hydroxide rate of negative 0.9 molar per second. And then for the formation of sodium phosphate and water, Both of them are going to be positive because they are products being formed, and they're also going to follow the same ratio. Since phosphoric acid to sodium phosphate is 1:1, it's also going to have a rate of 0.030 molar per second, but positive this time. And then similar situation with the water, which has a coefficient of 3, so it's going to be formed at a rate of 3 times. So therefore, it's going to be forming at a rate of 0.09 molar per second. Let's try another one. So let's consider the following reaction between solid magnesium and hydrochloric acid, making magnesium chloride and hydrogen gas. So say we have 1 gram of magnesium and we drop it into 50 milliliters of concentrated hydrochloric acid. And the magnesium is totally dissolved and the hydrogen gas stops bubbling after 5 minutes, indicating the end of the reaction. So if I wanted to figure out what the reaction rate for each of the reactants are, I'd first need to start with the reaction rate of the thing that I have data for, which in this case is the magnesium. So we can use that as our reference point. So first I turn my grams into moles. So that's 0.0412 moles of magnesium that are reacting. And I know that it's in a total volume of 50 milliliters. So if I divide those moles by the total volume, which is 0.05 liters, I get the sort of theoretical concentration of magnesium, even though it's not entirely in solution the whole time since it's dissolving in the acid. But that gives me sort of a theoretical concentration of 0.820 molar. And I know that the reaction took a total of 5 minutes. So that's going to be my time. I convert this to seconds by multiplying it by 60. So that's 300 seconds. And then I can divide the concentration change, which is going to be all of it, since we're referencing the end of the reaction as being when all the magnesium has dissolved and the hydrogen gas has stopped forming. So I divide the total concentration change by the time in seconds, and I end up with a reaction rate of 0.0028 molar per second. And since this is going to be for the magnesium, that's going to have a negative in front of it to indicate that is a rate of change of disappearance. And then for my other reactant, the hydrochloric acid, since it is being used up at a rate of 2 times that of the magnesium, I can just multiply that value by 2, and I get negative 0.0055 molar per second for the hydrochloric acid. So in order to get into more depth about how different rates of different chemical reactions can occur, we want to talk about something called collision theory, which is something that describes the basis of how a chemical reaction can happen in the first place. So if you see in this particle diagram here, we have our reactants, and they are moving too slowly, and they collide into each other, and they bounce off of each other, and nothing happens. And this is because you need to have two particles or two substances collide with enough energy in order for the bonds to be broken and new bonds to be formed. Because each of these individual reactants already has a stable configuration. You need some sort of high energy force in order to mix things up for those new reactions to occur in the first place. But sometimes the reactants aren't going to be facing the right way and they're still going to bounce off each other. So even if they have the right amount of energy, if the two things that need to form a new bond aren't able to come in contact with each other when the particles collide, we're also not going to get enough things to have a chemical reaction. However, if we have both of these in both at the right amount of energy and the right orientation, then we can have a chemical reaction. Because you can see here, the things that need to get close to each other are able to react. And in this case, this carbon is able to pull off one of the oxygens on this nitrogen, and we're able to get new products. So the overall idea here is that reactants need to collide with enough energy and the right orientation in order to react. And we call this prerequisite for a chemical reaction the activation energy. This is a certain amount of energy that any sort of reaction is going to need in order to happen in the first place. And we're going to be studying the rates and how the rates can be affected by these different ideas in collision theory based off of a lab that we're going to be doing. This is a lab that you're going to be able to do on your own because all it involves is Alka-Seltzer tablets and water. And you're going to be dropping Alka-Seltzer tablets in different temperatures of water. You're going to be combining multiple tablets at once. And you're also going to hopefully grind up a tablet and see how that affects it. And we're going to base all of these and evaluate the effects of these different variables on the rate of reaction by comparing them through the mechanics of collision theory. And sort of the questions that you're going to be asking yourself here is, what do you think would happen to the rate if the water was heated or cooled? So how's the temperature of the water going to change how the two chemicals within the tablet are able to react with each other? How the rate is going to be affected if we put twice the amount in? And then how do we think the rate is going to be affected if we grind up the tablet? Because the amount of kinetic energy in the solution itself is going to be a big effect. The amount of things in the solution as a whole is going to have an effect. Like more things might lead to more collisions. And then also we're going to want to consider the particle size of the solid itself. Since this is a reaction that is starting as a solid, the more of it is exposed might have an impact on the overall rate. But these are all things that you're going to experimentally determine yourself. And the rates of reactions, kind of based off of what we've been talking about here, depend on many factors and are highly influenced by the starting concentration of the solution. So in order to be able to predict and calculate the rates of a reaction and understand the kinetics, we're going to need a reliable law that relates all of these different components. And a good candidate for that is something called a rate law, which is an equation that describes the dependence of initial rates of reaction on the concentration of the reactants. So say we had this generic chemistry equation here. We have A plus 2B plus C making D. We can make an equation to represent its rate in the following manner. The rate is going to be equal to K, which is a constant, which I'll talk about in a second, times the product of all of the molar concentrations of our reactants raised to some powers. And I'll talk about what those powers mean in a second as well. And the rate that we're going to be calculating here is the rate of appearance / disappearance of the products and reactants in units of molar per second. So the rate we're calculating here is a general rate for the whole reaction. And if we wanted to know the individual rates of the reactants, we can figure them out based off of the coefficients. So we can compare the moles of the component per 1 mole of the whole reaction. So whatever we calculated as the rate here, for example, if we wanted to know the individual rate of 2b, we'd multiply it by 2. So like I said, the square brackets usually represents molar concentration. So in the rate law, we're looking at the product of the concentrations of all of the starting components, all of their initial concentrations. And then we have this constant K, which is called the arrhenius constant. And this constant is not going to be a number that you can look up. It's going to be something that's experimentally derived and specific to the reaction, because it's going to be taking into account those factors we discussed with collision theory. It's going to be discussing the activation energy. It's going to be discussing the temperature and how that affects the overall rate. And the units of K are also going to be variable depending on the nature of the rate law itself, because the rate needs to be in molar per second. So the units of K are going to need to turn whatever the product of all of these units are into molar per second. And I'm going to go over what I mean by that in a little bit. So another way to think about this, so see we have this diagram here. This is called a chemical energy diagram. And on the x-axis, we're tracking the extent of the reaction, the progress of the reaction. And on the y-axis, we're representing the potential energy, how much chemical energy is stored within the bonds of the chemicals that are reacting. So based off of the x-axis being time, we can assume that we start with our reactants and then we end with products. In this specific example, we are losing energy from reactants to products, which means we have an exothermic reaction. That's something we'll talk about more in Unit 6. And we have a delta H, a change in enthalpy associated with that. Once again, that is something we'll discuss more in Unit 6. But then we have this other part of the difference between this transition state and the products, which is labeled as EA, which is our activation energy. And what happens here is that A and B first need to obtain enough energy in order for the reaction to occur. We need to meet all of those prerequisites associated with collision theory. And then we form what's called a transition state, which is like an amalgamation of all of the reactants. Everything is crushed together into a little pile, and that allows those new bonds to be formed. It's that instantaneous moment as those two things collide, the big mess that it makes. And then as the two things bounce off each other, now they've formed their new bonds, and we have our products. But you can see that even though this reaction overall is losing energy, it had to absorb a certain amount of energy to happen in the first place. And like we said, this going to be associated with the temperature of the reaction, how much kinetic energy the individual particles have, and then also the sort of random orientation of the particles. The K value, the Arrhenius constant, can also be derived from an equation called the Arrhenius equation, where the constant is going to be equal to A, which is the number of molecular collisions per second with proper orientation. So this is sort of a mini rate kind of idea, times E to the power of negative EA over RT, where R is the gas constant and T is the temperature. So you can see that there's a relationship between the value of K and then the values of the activation energy and the temperature. Both of them are going to have an impact on K. And you need to be aware of this equation and aware of this relationship between activation energy and temperature and the Arrhenius constant, but you're never going to need to use this equation to solve for anything. So let's get back to talking about the rate law. So the last bit here are the x, y, and z exponents that are on each of these reactants. And these are called the rate orders. And if you add them all up, we get something that's called the total reaction order. And overall, what this means, a rate order is an exponent that describes how changing the concentration of a substance is going to impact the rate of reaction. And the rate order is always going to be unitless and determined experimentally. So let me summarize how different rate orders can affect the reaction. So if the rate order is 0, or a zero order reaction, that describes a reaction where changing the concentration has no impact on the rate. So if we were to double the concentration of the reactants, we'd see no effect on the rate. There'd be no change in the rate. If the rate order was 1, that means we have more of a linear relationship. So if we were to double the concentration of the reactants, we'd see a doubling of the rate. Or if we were to triple them, we'd see a tripling of the rate. And then if the rate order was 2, that describes more of an exponential relationship between the concentration and the rate. So if we were to double the concentration of the reactants, we'd see a quadrupling of the rate. Now, like I said, these are all things that we need to determine experimentally. So you need some data of a reaction and its overall rates in order to form a rate law that can describe it in more situations than just the experiment that you're doing. So an example of an experiment where we determine the rate order and the Arrhenius constant, the experiment will look something like this. So for that reaction we were looking at before, where we had A, B, and C as our reactants, we're going to do an experiment where we alter one variable at a time. So we have 3 reactants, and we want to see how changing each of their concentrations is going to affect the overall rate. So in our trial 1, we have all of our reactants with a concentration of 0.1 molar, and we measure a rate of formation of the product of 0.02 molar per second. And then in my trial 2, I'm going to keep A and B the same, so they're still both 0.1 molar, and I'm going to double my C concentration to 0.2 molar. And then from that, we see a change of the rate of times 4. So we doubled the concentration of C, and we had a quadrupling of the rate. And that actually tells us something about the rate order of C, since this seems to have an exponential effect, because we doubled the rate and we doubled the concentration and then we quadrupled the rate order. So that tells us that C is going to have a rate order of 2. Now let's look at our third trial. So in our third trial, we can compare the third trial to the first trial because A is not going to change, B is going to double, and then C is not going to change. So we have a single change in the B variable. We're doubling its concentration to 0.2 molar. And we see a doubling of the rate. We go from 0.02 molar per second to 0.04 molar per second. So that shows us that there is a linear relationship between the concentration change and the rate change for B, which tells us that B is going to have a first order reaction. And then lastly, for A, with trial 4, we can compare it to trial 1 because we're now doubling the concentration of A, we're keeping the concentration of B the same, and we're keeping the concentration of C the same. And you'll note that between trials 1 and 4, there's no change in the rate, which tells us that overall A is 0 order with respect to the reaction. So from this, we can start to get more of an idea of the rate law because we've now determined the order of each of the individual reactants. So for A, it was zero order, for B, it was first order, and for C, it was second order. And since something to the 0th power is just 1, we can overall remove A from the equation, which makes sense because in a zero order reaction, its concentration has no impact on the rate anyways. So since we have a rate order of 1 for B and a rate order of 2 for C, we can describe the reaction as being third order overall. So more of a cubic effect of the overall concentration to the rate. Now, this equation still isn't very useful yet, though, because I don't know K. So what I'm going to do here now is I'm going to use my data to solve for K. I have plenty of measured rates based off of initial concentrations. And if I know how their concentrations affect the overall change in the rate, I can plug in starting concentrations with the proper exponents, and then I can solve for K. So for example, let's use trial 3. It doesn't really matter which trial you have because they should all give you the same overall information. So for trial 3, I plug in everything into my rate law. The rate was 0.04 molar per second. I'm solving for K. I had a starting concentration of B of 0.2 raised to the first power because B is a first order component. And then C, I plug in 0.1 as my starting concentration, and I raise it to the second power because we determined that C is second order in the reaction. And if I plug this all in and solve for K, I end up getting a value of 20 for K. And I've assigned it units of inverse seconds and inverse square molar. I'm going to describe why that is in just a moment. But then this finally gives me my overall rate order. I'm now able to determine what the rate is going to be in any situation at this temperature under whatever starting concentrations of B and C that we go with. And since those units of K had to be whatever units could help my overall rate have units of molar per second, you can kind of use algebra as a guide here to figure out what the units of K should be. Since my overall rate law for this equation was rate is equal to K times A to the second power times B, and this needs to be molar per second overall, I need to consider the units of this side of the equation. So both A and B in their concentrations are going to be molar. So here I have molar squared times molar. So that means that overall, molar per second has to be equal to whatever K is times molar cubed. So now I need to decide what the units of K are going to be in order to make molar cubed turn into molar per second. So I need to add in the per second. There's no per second part on the product side. So that's where the inverse second part of the units comes from. And then I need to have 1 molar. But here I have 3 molars. So I need to get rid of 2 of them. So that means I need to also divide by molar squared. So that's why the units of K now are inverse second times inverse square molar, because this times molar cubed overall is going to give you units of molar per second. And this is going to be something you're going to have to evaluate for any rate law. So please make sure you understand this logic. So let's change gears a little bit. Rate laws tell us how changing the concentration of a substance affects its overall rate. But we'll notice that in most chemical reactions, the rate does not necessarily stay the same the whole time. Of course, it's going to in a zero order reaction because as the reaction proceeds, the dwindling concentration of the reactants isn't going to have an impact on the rate. But for first, second order, and above order reactions, there's going to be a large effect as the reaction proceeds because both of those types of reactions depend on the concentrations of the reactants, how many particles there are in the reaction to collide with. So that means as the concentrations dwindle, there's going to be less and less collisions, and the rate is going to change over time because as the collisions go down, the rate is also going to go down. So if we look at the rates as a function of concentration, we could see that at higher concentrations for first order, we're going to have a higher rate. And as the concentration decreases, the rate is overall going to decrease. And we have the same relationship for second order reactions, except that it's exponential instead of linear. And if we rearrange this data to now look at the time as a function of concentration, in a zero order, we're going to see a linear decrease in concentration because the rate isn't changing. It's going to be the same rate the whole time. For a first order one, you'll see it's a exponential decay because as the concentrations start to decrease, you're going to have less collisions, and therefore the rate is going to slowly decrease over time, even though there's a linear relationship between the starting concentration and the rate. And then for second order, it's also going to be exponential, but a little bit more severe. All right, so a rate law can help us predict the initial rate of reaction. So I mentioned the idea of an initial rate earlier when I was introducing rate laws, because the initial rate law is something that you can just kind of measure roughly. It gives you a good rough estimate of what's going on. But the rate law doesn't tell you what the concentration of any component is going to be at any point in time during the reaction. And you're not going to be able to track the rates decrease as the amount of reactants decrease. Um, so the initial rate is always going to be something kind of linear, but then as the reaction proceeds, it's gonna drop off exponentially, unless it's zero order. But even like first order decay, which usually has a linear relationship, has an exponential decay to it. And if you could see in this graph below, which represents a first order reaction happening, you'll notice that every 100 seconds, something happens in this data. After 100 seconds, we go from zero point 0.1 to 0.05 molar. So we've decreased by 1/2 in this 100 seconds. And then in the next 100 seconds, you'll also notice that now it's 0.025. It is now halved again. And then after another 100 seconds, it's at around 0.0125. Actually, no, that would be zero point 0.01 molar. My bad. But you can see here that every 100 seconds, the concentration is halving. And this is something that is indicative of a first order reaction, and it's something called a half-life. All first order reactions have this sort of exponential relationship where there's a set amount of time that we can measure where we can reliably predict that the concentration will be half of what it was before. And in order to help model this exponential decay, we use natural logs because logarithms are really good at turning exponential information into something that is linear. And then with a linear graph, we're able to come up with a trend line that is more easily to use. So both graphs here represent the same data, but you can see here that the concentration has been ln'd, it's been natural logged. And that turns our exponential graph, our curved graph, into a straight one. And with the straight graph, then we can make a y equals mx plus b type equation from it. Since we know that the y-intercept is going to be the natural log of our starting concentration, and the slope is going to be equal to negative k, which is going to be our rate constant. And it's negative because we see that there's a negative decrease in our concentration. We can now predict what the natural log of the A is going to be at any point in time based off of this relationship. And our overall equation to describe this is going to be the natural log of A at time t is equal to negative kt. So t is our x axis, the time, and then the negative k is our slope, and then our y-intercept is going to be the natural log of our starting concentration. So using this equation, we can predict what the concentration is going to be at any point in time just based off of this information. And this equation above here, this natural log equation, this is something called an integrated rate law. This is a rate law that takes into account the change of concentration over time. And like I said earlier, this is going to be useful to track the concentration of the chemicals at any point in time based off of its rate constant and the amount of time that has passed. And this equation here is specific for first order reactions. There's a different type of integrated rate law for zero and second order reactions, but I'll cover those later in the slides. And I want to go back to talking about first orders and half-lives, because that's going to help us talk more about this first order decay equation. So since first order exponential decay is correlated with half-lives, the half-life can be used to determine K, our reaction constant. So half-lives overall are described in the following way. So at time 0, we have 100% of our sample. After one half-life has passed, we can assume that half of the material has been consumed. So we should have 50% of our sample after one half-life has passed. After 2, we're going to have half of that. So we're going to have 25% of the total. And then after that, we're going to have 12.5% of the total. So it's going to get halved every time a half-life passes. And if we know what the length of the half-life is, we can predict what its concentration is going to be at any point in time. So for example, radioactive decay. This is the natural decay of nuclei. Over time, nuclei break apart due to that repulsion of protons in the center. They release a bunch of nuclear energy, and they fall apart into much smaller components. And for some elements, this is really long. For example, carbon's half-life is 5,730 years. So say I wanted to figure out how much of a 250-gram sample of carbon will be after it's left out for 11,460 years. So if we divide the amount of time passed by the half-life, we can determine how many half-lives it was. So in that case, this is 2 half-lives. So we can assume that it's going to half once, and then it's going to half again. So 250 grams is going to go down to 125 after halving once. And then after halving again, it's going to be 62.5. And the quick way of figuring that out mathematically is taking your starting amount and then multiplying it by 1/2 raised to the power of how many half-lives have passed. So in this case, 1/2 times 1/2. And say you didn't have an exact amount of half-lives and you wanted to determine based off of any 2 points in a first order decay, you can use the following equation where you have your starting amount times 1/2 to the nth power, which we're going to use to figure out how many half-lives have passed. And we can then make that equal to the final amount. So we can rearrange that algebraically to get the following equation, where n is going to be equal to the log of the ratio of the final amount over the starting amount divided by the log of 0.5. So for example, say we wanted to figure out how many half-lives have passed for a sample that started as 100 grams and is now 30. So we have the starting amount and we have the final amount, and we want to know how many half-lives has passed. So we can use this equation here. So we have n, the number of half-lives passed, is equal to the log of the final amount over the starting amount, so the ratio, which is now 30 over 100, divided by the log of 0.5, which is overall going to give us 1.74 half-lives. And this makes sense if we think about it logically, because if we start with 100 grams, after one half-life we would have 50, and after 2 half-lives we'd have 25. 30 is between 50 and 25, closer to the 25, so we can say that it's near its second half-life. All right, and say we had a first order reaction data, and we are tracking the concentration of substance A as it's reacting as a function of time. We can use the half-life from this data to calculate its rate constant with the following equation, where half-life is equal to the natural log of 2 divided by k. Don't worry, a lot of these equations that I'm talking about are going to be in the equation sheet that's associated with the AP chemistry test. Not the half-life equation that I just showed here, but that integrated rate law equation that I showed for the first order reactions, and then this reaction, or this equation here, are both going to be on your equation sheet. So back to what I was saying. So based on the data table below, I want to figure out what the arrhenius constant, the rate constant is for this reaction. And then I'm also going to determine what the units of K are. So if I look at this, I have increments of 30 seconds, and I can see what the measured concentration at each of those time points are. And the first thing that jumps out to me here is this 0.2 going down to 0.1, because that is a half. And we can see that in that time, 60 seconds have passed. I see another data point here, 0.05, that's half of 1, and that's at 120 seconds. And that's further proof that there is a 60-second half-life in this equation. So then I can use that with this equation here to calculate the value for K. And if I do that, 60 seconds is equal to ln2 over K. I can rearrange and solve, and my K is going to be 0.01155 inverse seconds. And I decided that the units were going to be inverse seconds because it is a first order equation. If you assume an equation where rate is equal to K times the concentration to the first power, and I want to make it molar per second, I already have the molar from the concentration, so I just need to add in the per second element. So that's why for a first order reaction, the K is going to be in units of per second. All right, so now that we know K, we can use that in conjunction with the integrated rate law that we talked about earlier to calculate the concentration of the reactant at a specific time in the reaction, and then also with any starting concentration that we want. We aren't beholden to the data that we collected earlier with the 30-second intervals. So let's say the same reaction is repeated, but now with a starting concentration of 0.5 molar. What will the concentration be after 88 seconds? So now we can use our integrated rate law. So the natural log of the A at time t, which is going to be A at time 88 seconds, is going to be equal to negative kt, so the rate constant, which we calculated as 0.01155 inverse seconds, times t, which is going to be 88 seconds, plus the natural log of the starting concentration, which is going to be 0.5 molar. So I could start solving. I plug everything in. And then I end up with the natural log of A at time t is equal to negative 1.7095. So now in order to get rid of this natural log part, I'm going to do e to the power of both sides because that will undo the natural log and give us just A at time t, or A at time 88 seconds. And that's going to be equal to e times the power of negative 1.7095. And then overall, we're going to have a concentration of 0.181 molar at the end. And if you think about this, this also makes a lot of sense because we determined that this reaction has a 60-second half-life. So if it started at 0.5, after 60 seconds, we'd expect it to be 0.25. After another 60 seconds, we'd expect it to be 0.125. And the 88, that's between 60 and 120 seconds. So we can assume that the concentration is going to be a little bit past what it would be at the end of the first half-life. So 0.181 molar makes logical sense. So say we had a second order reaction instead of a first order reaction. We're going to have to model this one a little bit differently mathematically because if you were to take second order data and do the natural log of it, you still wouldn't end up with a linear relationship. However, if you used an inverse of the data, you would get a linear relationship that is positive. But that's going to be good enough to write a y equals mx plus b type equation that we can use to predict concentrations with. But this time it's going to be 1 over a at time t, so whatever the y-axis component is going to be, is equal to kt, so a positive version of the rate constant times t, plus 1 over the starting concentration, so the y-intercept. And we can go through the same sort of algebra to calculate what the concentration is going to be at any specific time, assuming that we know the rate constant, which we probably have to figure out somehow experimentally. If we had a zero order reaction, it's actually a little bit simpler. Since the rate doesn't change as a function of time, we can assume that it has a negative relationship between concentration and time already. So the slope is just going to be negative k. And since we don't need to manipulate the data in any way, the y-intercept is just going to be a at time t. The y-axis value is going to be a at time t, and the y-intercept is going to be a at time 0. So it's much easier to predict the concentration at any point in time using a zero order integrated rate law. So to summarize here, if the concentration decays linearly as a function of time, we know it's zero order. If it decays exponentially and has a half-life, it's first order. And if it's exponential and doesn't have a consistent half-life, we know that it's either second order or above. And depending on the order of the reaction equations, we're going to use different equations to evaluate their concentration change. So as we covered, the zero order is going to be A at time t is equal to negative kt plus A at time 0. For first order, it's going to be the same thing, except that the concentrations are now natural logged. And then for the second order, our concentrations are now inversed, and our k has become positive. So based off of the type of data that we're looking at, you're going to want to use the correct rate order equation. And all three of these rate order equations, I believe, are on your equation sheet. Maybe not the zero one, but I think that one's conceptually easy to know just based off of the relationship between starting and ending concentrations. All right, and that's going to wrap up part 1 for Unit 5. So I'll see you in the next video.